Harder vectors with geometric proofs. So we're going to jump straight into an example here. And we need three vectors, first of all. We're going to look at vector P being 4i plus j, vector Q being 3i minus 3j plus 4k, and vector R being I minus 2j plus k. And to visualize this, it's probably best to draw a diagram. So let's go ahead and draw some axes in. So we're going to have our x-axis, our y-axis, and z. And let's go ahead and draw some of these vectors in. So 4i plus j, that's just going to be moving along the x-axis 4 units and then y-axis 1 unit in the positive direction. So this vector will end up maybe somewhere here, where this distance was 4 and this distance was 1. Now our next one moves 3i minus 3j, so minus 3, and plus 4k. So we've gone here. So following these out, we're looking maybe somewhere about there. So mapping out this one first, and then moving up 4 units, so maybe about there. So let's just draw that vector in. And we'll draw our other one in. And finally, we've got R, which is I, so it's going to be a distance of 1, minus 2j, plus k, so come up 1, so maybe about there. Now, so our first one we'll call P, second one we'll call this point Q, and we'll call this point R. And our proof that we need, so we're required to prove that triangle PQR is right angled, which means that we need to take the points that all these form, join them together, and show that that triangle there is right angled. Okay. So in order to do this, we probably need expressions for the vectors RQ or QR, but I'm going to go with RQ, QP, Q to P, and R to P. It doesn't really matter which direction you go with, but I've chosen those. So we're going for R to Q, Q to P, and R to P. Now all of these vectors, R to Q can be expressed as O to Q minus O to R, using some simple vector subtraction. QP can be O to P minus O to Q, and R to P can be OP minus OR. And remember, these original vectors can be thought of as OP, OQ, and OR, because they're all from the origin. And to get our vectors here, all we need to do is subtract the components from each other in OQ and OR, which we've got over here. So for example, in the first one we're going 3i minus I to give us 2i. Then we're going minus 3i minus 3j minus 2j. So it'll be 3j minus 3j plus 2j, which will give us minus j. And then we've got 4k minus k, which is 3k. Let's do something similar. So we've got OP minus OQ. So we're going to have 4i minus 3i, which is I. We're going to have j minus 3j, which will be 4j. And we're going to have 0 minus 4k, which will be minus 4k. RP, so we're going to have OP, so 4i minus I, which will be 3i. J minus 2j will be plus 3j. And 0 minus k will be minus k. And now we've got expressions for the vectors that are the sides of the triangle. And if we want to show that this triangle is right angled, we know that the dot product of two of these vectors is going to be 0. So let's take a stab and find the, well, I've already done it, but let's go ahead and find the dot product of R to Q and R to P. So that's just going to be all the components multiplied by each other and added together. So RQ and RP are these two here. So we're going 2 times 3 plus minus 1 times 3 plus 3 times minus 1. So we're going to get 6 minus 3, which is 0, which will show that therefore these vectors have to be perpendicular since their dot product is 0, and therefore the triangle must be right angled. We also can find the area of the triangle. If we know it's right angled, we can just get the magnitude of these two sides and use half the base times the height. So let's go ahead and do that. So we need the magnitude of R to Q. We need the magnitude from R to P. So magnitude of RQ is just going to be the square root of 2 squared plus minus 1 squared plus 3 squared, which is going to be root 14. And the magnitude of RP is just going to be 3 squared plus 3 squared plus minus 1 squared, which is just going to be root 19. And the area is just going to be half the base times the height. So we get half of root 14 times root 19, which is just a half times root 266. Let's look at another proof. So let's draw out a square. Using the XY axis. And we want to prove that the midpoints of a square, when joined together, also form another square. That's what we're required to prove. So let's write some things down and just label some things to make this a bit easier. Let's call this point A, this point B, C, and D. We'll call this point E, F, G, and H. And let's draw in some vectors just to make things a bit easier. So we're going to turn all the side lengths into vectors. All ones going up like that. So trying to keep our vectors parallel when we can. Let's make all these ones point this way. And then inside the square we'll go around in this direction like so. So let's write some things down. Let's first of all, let's also call the length of this, we'll call this vector A, and we'll call this vector B. So the side lengths of the original square. And we can say that the magnitude of A is going to equal the magnitude of B, because we know the original square is a square. We also know that the dot product of A and B is going to be 0, because since it's a square, they have to be perpendicular to each other. We also know that we're constructing this internal quadrilateral at the midpoints, so we're able to write quite a few expressions down. So let's look at the vector AE, which is just this one down here, going from A to E. And we can easily say that that's half of vector A. And that'll be the same for vector EB, the same for vector GC, and the same for vector DG. Let's also look at the vector BF, and in a similar way we can say that's half of vector B, which is going to be the same for vector FC, same for vector AH, and the same for vector HD. Now we would like expressions for the vectors joining the midpoints of the original square. So we can say that the vector HE, this is our first vector down here, is actually just equal to the vector AE, A to E, minus A to H, using our simple vector subtraction rules. So we've got vector AE minus AH gives us this vector HE. And we have expressions for those. We know that AE equals a half of A, and we know AH is a half of B. So this is just a half outside of A minus B. In a similar way, we can get an expression for EF using vector EB minus vector BF, and this will just be a half of A plus a half of B, and we get a half of A plus B. You get an expression for FG, it's just going to be FC minus GC, which is a half of B minus a half of A, and we get a half outside of B minus A, which we can actually rewrite, take a half out as a half of A minus B. Let's get an expression for GH. This is going to be minus DG minus HD. So we get minus a half A minus a half B, and we get minus a half of A plus B. And they're all the four side lengths of our quadrilateral formed inside the square. And we can see that HE and FG are the same, they only differ by the negative sign, which means that they have to be parallel, because a negative sign in front of a vector, all it does is flip the vector in the same direct, it flips it in the opposite direction, so it means they have to be parallel. So HE and FG are parallel, and we can see the exact same thing with EF and GH. They're exactly the same, they only differ by the negative, which just means they're going in opposite directions, which we can see. So because EF goes this way and GH goes this way in exact opposite directions, but they have to be parallel. So all we conclude from here is that the shape now is a parallelogram. So we need to keep proving some things to prove that it's actually a square. So right now we've proved that it's a parallelogram, but we need to keep going. And another thing we can do now is show that the dot product between two of the vectors is 0, and that'll prove that we have a 90-degree angle. And let's go ahead and do that. So let's find the dot product of HE and EF. So HE is just a half A minus B, and we're going to dot product with a half A plus B. So the half and the half will be a quarter. Then we've got A dot A plus A dot B minus A dot B minus B dot B. A dot B and minus A dot B cancel out. We have a quarter times A dot A when we have the same vector dot product. That's the same thing as the magnitude of that vector squared, minus B dot B, which will be the same thing, the magnitude of that vector squared. But we know originally that the magnitude of A and B are equal to each other because the original one's a square. So we get a quarter times 0, which is a quarter, and we've just shown that the dot product of these two vectors is 0, which means they are perpendicular to each other. So at this point, we've upgraded our knowledge from it being a parallelogram to a rectangle because we've got a 90-degree. We just don't know if all the sides are equal. So if we can prove that two sides are equal to each other, we can successfully prove that it's a square. It's going to need a bit more room. Okay, so let's find the magnitude of HE. That's just going to be a quarter times the square root of A minus B squared. And we're going to find the magnitude of EF, which is going to be a half times the square root of A plus B all squared. So we're going to get a half square root of, this is going to be A dot A minus 2 times A dot B minus B dot B. A dot B, they're perpendicular to each other, so that's going to be 0. A dot A, we can write as the magnitude of A squared. It's meant to be plus B dot B, so for that one, plus B dot B is going to be the magnitude of B squared. We know that the magnitude of A squared equals the magnitude of B squared, so we're just going to rewrite the magnitude of B squared as the magnitude of A squared. It's a half outside of the square root of 2 times the magnitude of A squared. Now, the square root and the square on the magnitude of a will cancel. So we'll just be left with root 2 on 2 times the magnitude of a. So we're going to do something very similar for EF. So we're going to have the square root of a dot a plus 2 times a dot b plus b dot b. That's going to be 0 because they're perpendicular to each other. And hopefully you can see we can take a bit more shortcuts this time. This is going to be the magnitude of a squared plus now b dot b is the magnitude of b squared, but that's also equal to the magnitude of a squared. And we're going to get the exact same thing, a half times the square root of 2 times the magnitude of a squared. Those magnitudes will cancel out, and we're just going to get root 2 on 2 times the magnitude of a. And they're going to be equal to each other, and now we can confirm that that quadrilateral inside the original square is also a square.